Water can exist in 3 different states. In the iceberg, it's solid. In the sea, it's a liquid. In the surrounding air, it's a gas. Solid, liquid and gas are the 3 states of matter. Solids have a definite shape. A block of ice takes the shape of its mould. As it melts, it changes. The water spreads out and fills up the container. All liquids behave this way. They flow and find their own level. Gases spread out even more, filling any space available. The way solids, liquids and gases behave gives us clues about how their particles are arranged. In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. But how do we know the particles in a gas behave this way? Some of the evidence comes from looking at how smoke appears under a microscope. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light enables it to be viewed under a microscope. It looks like tiny jittering points of light. When a straw burns, the smoke produced is mostly bits of carbon which haven't combusted. Under a microscope, they catch the light and appear to glimmer. But why do they randomly dance around? The movement of the smoke is caused by collisions with invisible air particles. As the air particles move about, they knock the smoke first this way, then that. Particles in a gas move randomly and quickly. Flowers produce pollen, which is a very fine dust, easily brushed off by a finger. Nearly 200 years ago, it was this dust which first gave us clues about how particles behave in a liquid. In the 1820s, the botanist Robert Brown was carrying out a study of pollen grains. He decided to crush the pollen and suspend the grains in water. But to his annoyance, the pollen continually jittered around. Today, we can best see this effect by looking at tiny carbon particles instead. A drop of carbon powder suspended in oil is placed on a slide and viewed under a microscope. Just like the smoke, the carbon is dancing around. Brown didn't know why this movement occurred, but we now believe it's caused by the motion of particles in the liquid. The carbon is being pushed around by collisions in the oil. Water vapour spreads out into the atmosphere. It's carried by the wind, but it can also spread out of its own accord by a process known as diffusion. Invisible gases behave in the same way. The particles in a gas move randomly in all directions. This helps explain why a gas diffuses from one place to another. You can see diffusion happening on a small scale in the lab, using bromine, an orange-coloured gas. Place a jar of air on top of the bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the two gases mix. After half an hour, both containers have a uniform colour. It takes time because the air and the bromine molecules are colliding with themselves and each other. So what would happen if there was no air for the bromine to bump into? All the air has been removed from this apparatus, apart from the flask containing bromine, which is isolated by a tap. Open the tap and it spreads immediately. Watch again. In a vacuum, there's no air to collide with. The bromine diffuses much faster. See how slow the diffusion is when the flask is now full of air. It takes several minutes to get just this far. This simple setup can be used to compare the rate at which different gases diffuse into air. Nitrogen dioxide gas on the left is similar in colour to bromine on the right, but bromine molecules are much heavier. The lighter nitrogen dioxide diffuses more quickly. We can also compare the diffusion rates of other gases. Ammonia and hydrogen chloride gas are colourless, but when they meet, a white cloud of ammonium chloride forms. A piece of cotton wool soaked in concentrated ammonia solution provides ammonia gas. Concentrated hydrochloric acid provides hydrogen chloride gas. Place the two pieces of cotton wool at opposite ends of a tube and the gases spread out. You can compare the speed at which they approach each other by looking out for a cloud of ammonium chloride. After less than a minute, a white ring begins to form, marking where the gases meet. The white solid is closer to the hydrogen chloride end of the tube, on the right. So which gas has travelled faster? Another way of monitoring the progress of the gases is to run a piece of damp indicator paper along the tube. Hydrogen chloride gas turns it red, ammonia turns it blue. Why does ammonia travel faster? Diffusion also happens in liquids. Drop potassium permanganate crystals into water and they begin to dissolve. The purple solution then spreads out. It diffuses through the water. These three tubes containing water are immersed in baths at different temperatures: 0, 20 and 70 degrees Celsius. A crystal of potassium permanganate is placed in each. After 10 minutes, diffusion in the hot water is almost complete. Why does the rate of diffusion appear to be quicker at higher temperatures? What other factors might be involved? When a solid gets warm enough, it melts. To explain what's happening, imagine you can see how the particles in a solid are arranged. They're in a fixed framework, vibrating but not straying far from their main position. When energy is supplied, the particles vibrate more violently and become free to move. The solid changes into a liquid. Melting involves a transfer of energy. This can be illustrated by putting an ice cube in a sealed container, leaving another one empty. The air on the left is at 25.5 degrees Celsius. As the ice melts, it takes energy from the surroundings. The temperature of the air in the right-hand container has fallen by about 3 degrees. Energy is also needed to change a liquid to a gas. So, what's happening to the particles this time? In a liquid, the particles are free to move around. Heating causes them to move around more quickly. Those which have enough energy escape from the liquid, forming a gas. This is evaporation. Ether evaporates at room temperature. It's taking energy from the surroundings and disappears in less than 5 minutes. It's possible to see how different liquids take heat from their surroundings using thermometers wrapped in string. They all start off at room temperature. The string absorbs the liquids. Number 1 on the left is a control. Number 2 is dipped into water, 3 into ethanol and 4 into ether. As soon as the string leaves the liquid, evaporation gets underway. The temperature of thermometers 3 and 4 quickly begins to drop. As the liquids evaporate, they're taking energy from the string, the air, and even the bulb of the thermometer. So, which has taken most energy from its surroundings? Liquid 2, 3, or 4? Gases can also be changed into liquids. For this to happen, they need to be cooled. Liquid nitrogen is extremely cold. Immerse a balloon full of air in it and see what happens. The balloon shrinks and becomes brittle. Inside, you can see a liquid. It's liquid air. This time, the balloon is filled with carbon dioxide gas. Immerse it in liquid nitrogen and it cools rapidly. What's inside the balloon this time? If a gas gets cold enough, it changes into a solid. This is solid carbon dioxide. See how it changes back to a gas at room temperature. Some of the evidence comes from looking at how smoke appears under a microscope. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light enables it to be viewed under a microscope. Changes. The water spreads out and fills up the container. All liquids behave this way. they flow and find their own level. Gases spread out even more, filling any space available. The way solids, liquids and gases behave gives us clues about how their particles are arranged. Water can exist in 3 different states. In the iceberg, it's solid. In the sea, it's a liquid. In the surrounding air, it's a gas. Solid, liquid and gas are the 3 states of matter. Solids have a definite shape. A block of ice takes the shape of its mould. As it melts, it changes. In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. But how do we know the particles in a gas behave this way?